talks about area, then 5.3 is rising sums. So we're gonna do 5.3, but while we're doing it, we'll also talk about 5.2. 5.2 is built into 5.3. So really, I can call this 5.2 and 5.3. Maybe this is 5.2 and 5.3. 5.2 was area. These rhyming sums actually find area. So here's what we're going to start out doing. We're going to approximate the area between the function f of x equals x squared and the x-axis from 0 to 2 using 4 rectangles. What you think?
That's how the name of this class is with analytic geometry.
Oh, it's calculus with analytical geometry.
Yeah,
Wow, you're thinking.
4 triangles or rectangles, sorry.
It is. There's a lot of geometry involved here that we don't know about. But to help me with my graph here, I'm going to use the calculator to graph it so I get a nice graph of y equals x squared. So y equals x squared. I'm going to do zoom 6. Actually, it said from 0 to 2. Huh? So I'm going to change this window and go from 0 to 2. But you know what, maybe I'll go from -1 to 3, just so we get a little bit before and a little bit past. So -1 to 3, and then I'll do zoom fit. Then give me the y-axis. So I did. Maybe I better change this y to go down to -1, so we can see the x-axis. I'm just trying to get a decent graph there. So I'll take a picture of that. Okay, so what we're going to do here, here's the graph right here. This is the graph of y equals x squared. Or f of x equals x squared. Say, we want to approximate the area between this curve at the x-axis from 0 to 2. What we're going to do is draw some rectangles underneath. So if we want 4 rectangles, I want to make them all so they have the same width. What width should I use? A half. All right, if I use a half, it goes 0 to half, half to 1, 1 to 1 and a half, 1 and a half to 2. So we break it down like this. Okay, so we want this is 0, this is a half, this is 1, this is 1 and a half, or 3 halves, I guess I'll say. Easier. You guys, the easiest way to figure out if you want them all to have the same widths is just to take the change in x divided by how many rectangles. All right, we're going from 0 to 2, so the change in x is 2 minus 0. And then just put that over the number of rectangles. So put 2 over 4, and you get a half. So now I can actually draw some rectangles here. I'm going to go from the right side here, I'm going to go to this, and I'm going to draw a rectangle. I'm going to go from here, I'm going to draw a rectangle there. I'm going to go from this, draw another rectangle. Here, draw another rectangle. So what it is, I just use the right side of the rectangle, the width here, to find the height of the rectangle. There's 4 rectangles. If I can find the area of those 4 rectangles, I can approximate the area between the function and the x-axis. So the area of a rectangle is just width times height, right? So here I can approximate this first. I'll say this first rectangle, the width is a half, and then the height is just a half square. Right? Because I went over here and I went up to the function's x squared, so if the x was a half, the height was a half squared. The next rectangle has a width that's a half. But what's its height? 1 squared, right? Because on this one I used 1 for the x of my height. And the next rectangle's got a width of a half, and its height would be 3 halves squared. got a width of a half. And then we use 2 for the x to find the height, so then this times 2 squared. Now notice in everything here, I've got a half, right? I've got a half, a half, a half, a half. Might be easier to factor that half out. Then I'm just left with 1/2 squared, which is a fourth, plus 1 squared, which is 1, plus 3/2 squared, which is 9/4, plus 2 squared, which is 4. So the area is 1/2 times 1/4 plus 9/4 would be 10/4. And then I'd have 5, which is 20/4. 10/4 plus 20/4 would be 30/4. So I sort of combined some stuff there. I said, okay, 1 plus 4 is 5. I knew these were over 4, so I thought 5 is 20 over 4. And then 1/4 plus 9/4 is 10/4, plus 20 over 4 is 30 over 4. And then 2 goes into 30 15 times, so we get 15 over 4 square units. Why do we have what? Like here? Here, here, and here. Because the area of a rectangle is, its length times its width. So this one, I said, I did width times length. I said this one, the width is a half. The height is whatever this is here. And I drew this line to the function. The function was x squared. So if I drew a line when x is a half, this line is 1/2 squared. This line is when x is 1, it goes to the function, so it's 1 squared.
So it depends on the function.
Depends on the function, yeah. Now, because what do we know about this estimate for sure? It's too big, right? Every one of these rectangles we drew went above the function. What if, maybe I'll do it in green here. Or you know what, maybe we'll just do another. What if we did this and we made our rectangles to the left instead of to the right? Now what if we took this same graph this time when I draw the rectangles, so here's a half, 1 1.5, 2. What if this time I came from here to draw the height? This first one, I'd start when x is 0, make the rectangle, it really is a rectangle. This one here, I'd go from a half up to the function, draw my rectangle over. Here I'd go to the function, draw my rectangle over. Here I'd go to the function, draw my rectangle over. Right. If I draw the rectangles here, what do we know about this approximation? It's too small, right? Because all the rectangles are under, we're missing some stuff. Then we know for sure the actual area is in between the two. But to find this, in this one, every rectangle, the base is going to be a half, right? You notice how when we did this before, we could factor out that 1/2. Let's go ahead and do that. Instead of doing a half times an x squared plus a half times an x squared, let's factor out that change of x, or all the widths. All the widths are a half. Then all we have to do is add up the heights. What's the height of this first one? Yeah, I want to show the steps at 0 squared, right? What's the height of the next one? You know, 1/2 squared. Right, because we went, here was 0, and this one was a half. This was 1, this was 3/2, and this was 2. So first we used 0 for our x, then we used a half, then we used 1, then we used 3/2. So that'd be plus 1 squared plus 3/2 squared. So the area would be about 1/2 times 0 plus a fourth plus 1 plus 9/4. And so it's a half times here we get 10/4 plus 4/4 would be 14/4. 2 goes into 14 7 times, so 7 units. Square units. So we could, yeah, or that would get us probably even closer. But we can say with certainty that this, is that one of the words you make fun of me? It's height. I would say length and width instead of height. Was I saying height? But we can say with certainty that the actual area is somewhere in between those two. Right? And if we wanted to be more accurate, what would be the best way to be more accurate? Draw more rectangles. Right? If we drew more rectangles, we can get closer and closer to not having stuff above or below. The more rectangles we draw, the more accurate our approximation. George Friedrich Bernhard Riemann. This guy was a German mathematician. He did his most famous work in the areas of non-Euclidean geometry, differential equations, and number theory. It was Riemann's results in physics and mathematics that formed the structure in which Einstein's general theory of relativity is based. But these guys figured out an integral, an antiderivative, does, that's what we're going to work our way to, it does what we want to do here. It theoretically draws an infinite amount of rectangles in here, adds them together, and finds the actual area. Watch this. This is one of my favorite things to do on the calculator. I don't know if we got it next. Okay, see up in calculate here, we've been doing this. Hey, don't steal my thunder. Okay, so if I calculate an integral number 7, right, we wanted the area in between 0 and 2, so I'll ask it to start at 0 and go to 2. Now it's going to draw an infinite amount of rectangles and add all those areas together and tell us the exact area is 2 2/3. I think I'd have to concur with your conclusion. Hey, guys, this right here, 15 over 4, let's see, that's really 3 and what, 3/4? And the other one we got was 7/4, that's 1 and 3/4. Right, we said the actual area was somewhere in between that, and this is 2 2/3, that's in between those two things.